Yeah. Yeah. Yeah, so I'll have something to say about that today also. Okay, so I'll start this because actually I'm stealing time from Ashraf's talk. So dare not delay any further because that will leave even, you know, less time for Ashraf to complete his stuff. So just a reminder, so this is the part 2 of the talk that I was giving yesterday. So the talk was titled, if you remember, Markov, Ziff, Shannon, or Markov, Shannon, Ziff. And I only had a chance to talk mostly about Markov and a little bit about Shannon, and then I ran out of time. But fortunately, I ran out of it at the right point because this was a natural break point. Because I spoke all about Markov processes and how you use Markov process to model language. And now I'm going to switch gears a bit and talk about information. Okay? So whereas in the previous talk, I was talking about how you can use stochastic process as a way of modeling a complex system. Now I'm going to ask questions about how you can measure the information content of a given string and what can it tell us. So the person who gave us this method of measuring information quantitatively, so you can assign a number to a particular set of strings, or you get a like a alphanumeric sequence, and then you ask, okay, how much information is there? Okay, that person is Claude Shannon. Okay. So he was an engineer in Bell Labs, and as you can probably guess from this photograph, a fun guy, right? So guess what he's doing here? Sorry? He's juggling, but not just juggling. He's doing something else. He's on a unicycle, so he's simultaneously balancing on an unicycle as well as juggling. And in fact, he has written a very, very serious piece of article on how many balls you can juggle. So, like his interests spanned a wide range. He is one of the first people to build a chess-playing computer. Okay, so this is right after the first electronic computer was built. So, one of the projects he did in AT&T Bell Labs was how to make a chess-playing computer. So he has, in one of the first ever technical papers on how do you actually design a machine which can actually go through all the, possible decision trees for playing a game of chess. Then he is one of the first people to work with robots in a sense. So he built this, robotic mice and made them go through mazes. So, the usual psychological experiments is where you train a mice to run through a maze. The idea is like, there's this very complicated maze and the mice must find out a particular door where food is located. And, whether the mice is able to learn its way through the maze is considered to be quite a, significant achievement. What he did was he actually constructed mechanical mice which can run through mazes, and the idea was that can you make this mechanical mice learn what is the best way to run through these mazes. So this would be in the 60s that he's doing all this, right? So and then of course he over top of this he did this fantastic piece of work, which is what I'm showing him here for, the so-called theory of communication, in which he, among other things, he proposed a way of quantifying information. Okay. So if you're interested in learning about Shannon, there are wonderful books out there, one by Sony and someone else. which kind of gives the spectrum of interests he had. So essentially what we are concerned today is not his other interests, but this particular article that he wrote in 1948 called A Mathematical Theory of Communication, in which he introduced a concept of information entropy. Okay. So this, he said, is essentially related to how much you can compress information when you're trying to send it efficiently across from one point to the other. Now, why was he interested in this? Well, for one reason, his employers were very interested in this issue. Okay. He worked with AT&T Bell Labs. Okay, and what is AT&T famous for? Telecom, right? So AT&T were actually building this, transcontinental telephone system at that point. And the idea was that how can you compress the information that you're sending across this, telephone lines, so that, you can put across as much information as possible through the fewest number of transcontinental lines. Okay? So you usually don't have like, a dedicated line going from house X in, let's say, New Jersey to house Y in California. So instead what you will do is you will take all the telephone lines from a particular neighborhood in New Jersey, then bring it all together in a particular, local exchange, and then take a trunk line from there to somewhere in, let's say, Albuquerque, and then from there Albuquerque run another trunk line to, let's say, Los Angeles, and so on. And then from the Los Angeles, then again lines will go to individual houses, let's say. So if you want to send information across from, let's say, a house X in New Jersey to a house Y in Los Angeles, you essentially first, go to the nearest exchange, then you send it to the trunk line, and you want to save, the resources. So you want to have as many messages going through this trunk line as possible. So you want to have an efficient coding of this information so that they take up less space. So that way you can pack more information. Okay? So the question that his employers asked Shannon was, how much can we compress a piece of information to the point where we can actually recover what was originally written? Okay? Now you might say, okay, what do we mean by compression? Now, of course, anybody of you who have run a compression algorithm on your data will know what I'm talking about, right? So there used to be this thing called pkzip, and now it's gzip, and so on. I'm sure, all of you have used gzip or pkzip. So what is it that we are doing? So we are taking our photographs, our, whatever, MP4 files, MP3 music files, and so on, and we are basically running it through some kind of a software. We don't know what's going on inside it, but at the end of it, we expect to get something which is smaller than the total of all the files sizes that we had put in the input. Okay? So, there is something going on in this data compression algorithm which essentially reduces the total size of the data that we had given as an input. Okay. So one of the ways in which you could think of compression is like this. You take out any information that could be redundant, that you could actually recreate just by knowing whatever is actually out there. Example, again that thing that I mentioned yesterday. So suppose you are sending across this message. Okay, so it has how many characters? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay. Now, in the olden days, when you were you would send telegrams, it would cost you to send each character. So you'd try to make your thing as compressed as possible, message as compressed as possible. So suppose you want to compress this. That is, you want to use as few letters as possible in the overall message. How can you write it? Simplest thing is you get rid of all the vowels. and you'll still be able to make out what I mean. All right. So how much have I compressed? So instead of 23, 1, 2, 3, 4, 5, 6, 7, 8, almost reduced it by half. Okay. So, this is not a serious data compression algorithm. Actual data compression algorithms are much more sophisticated than that. But you can see that there's a lot of redundancy which we can try to get rid of. Okay. Same thing happens with images. Okay. So I can take an image and I can say that, look, if you think of the image as basically a grid, okay, then each grid is of a particular color intensity, and this color intensity can be encoded by a particular number. So this could be 123, this could be 124, this could be 2, this could be 1, this could be 0, then this again could be 120, and so on. Okay. So basically, I have, so what do these numbers essentially represent? The particular color intensity that is there. I mean, imagine it's a black and white image. Okay. So maybe essentially black, complete black indicates that it's 0, and complete white indicates it's 256. So basically you can have this entire range of white to black encoded, and so these will be gray levels. So the entire photograph, which is a black and white photograph with shades of gray, can be encoded as a table of numbers. Okay. So then you can try to see, look for redundancies. So for example, you would find that very often you will have entire patches of color, for example here, which is roughly of the same color intensity. Okay. So let's say it's a picture which looks like this. Okay. Okay. So this part is some, object in the foreground which is completely black. So you know that this is, very close to 0 to 10, let's say. So you could argue that, look, I don't really need to give all these individual intensities. I could just argue that I could just give the boundary and say that everything to the left of this is essentially, let's say 5. Okay. So that's one way of compressing. Okay. Again, real data compression algorithms are way more sophisticated. Okay. I'm just giving you an argument. All right. So now, what is the maximum you can compress? Okay. That's the question that AT&T asked Shannon, and trying to solve this problem, he basically derived this famous coding theorem, where by using the concept of information entropy, he could give, like, what is the maximum you can compress a given piece of information. Okay. Now, for those of you who are more interested in digging deeper, I would actually, strongly endorse that you see this wonderful movie. As you can see, it's really old. It was made in 1953, made by the famous designer duo Ray and Charles Eames, who are also famous for this Powers of 10 movie, one of design classic. And this is actually available on YouTube, so you can actually, I won't be able to play it, unfortunately, because of lack of time, and it's quite a long movie, but it gives you a wonderful idea of what Shannon's theory is all about. So if you are interested, please do go and take a look at this movie, and the slide would be available online, so you can just use this YouTube link to watch it. All right. So using this coding theorem, essentially Shannon showed that information is just as physical a variable as, let's say, mass, length, time. So just as you can measure mass in grams, or length in meter, or time in seconds, you can measure information also and give it in terms of a particular unit, which is called the bit. The bit is an acronym. It stands for binary digit. Okay. So information is one bit if that information basically just tells you whether it's one thing or not. It's basically just a yes, no answer to a yes no question. So just to give you an example of this, okay, so we have heard all about bitcoins, but sorry, this is like really, we have all heard about Bitcoin, but today I'm going to talk about the coin bit. That is the coin represented as a bit. Okay? So if the coin comes up tails, it's one state. If the coin comes up heads, it's another state. Okay? So I can ask the question, is the coin, has the, after a coin toss, has the coin come up head? That's a yes no question, right? So if you tell me yes, I'll know that it's come up head. If you say no, it comes up tails. So basically I have answer to a yes no question. So the information that is contained in this answer, that has the coin come up head or not, has the information content of one bit, because it's the answer to a yes no question. Okay? Anyone played the game of 20 questions when you were a kid? Okay, so the game of 20 questions is two people play this game. So one person tells the other, okay, I've thought of something. And the other person has to guess what this person has thought of by asking up to 20 questions, and the person will only answer you yes or no. So it has to be a yes no question. So for example, suppose I say, okay, I've thought of something. Okay. And you say, is it a person? No. Is it a place? No. Is it a book? Yes. Is it a novel? No. Is it a science book? Yes. Is it written in 20th century? No. Is it written in 18th century? No. Is it written in 19th century? Yes. Is it about physics? No. Is it about biology? Yes. Sorry? Yeah. Good. Fantastic. So you can now basically figure out how many bits there is, right? By looking at how many yes. I mean, of course, I could do it even more optimally. Maybe I'm particularly stupid and I use more questions than I needed to. So I can ask, okay, what is the smallest number of yes no questions I need to ask to guess correctly what is the answer? And that will give you the number of bits. Okay. So now, suppose I have a random coin. I mean, a perfectly fair coin. So again, I love this thing, right? Because you always have your demo right in your pocket. So I take this, 4 pieces of coin, and I say that, okay, I will toss them, and I ask you, what is the outcome? Okay. So how will you answer me this question? So you will ask, okay, is the first coin's outcome head? And I say, yes. Okay. So then the first entry is 1. Is the second coin's outcome a head? No. Okay, so then that means it's 1, 0. Star, star, we don't know. Third coin, head? Yes. Okay, 1, 0, 1, star. Is the last coin's outcome head? Yes. So then 1, 0, 1, 1. So that means using 4 yes no questions, you basically work out what is the outcome of 4 coin tosses. Okay. So what is the information content of this? 4 bits, right? All right. So it's that simple. Well, now what Shannon did was, he said, okay, then I can think of information, or how to measure information as basically what you are measuring is how much surprise do I get when you reveal to me the answer. So suppose, I am asking you the answer to a certain event. Okay. So for example, okay, nowadays, of course, you have to be very careful whether you're asking, politically charged or ethically charged questions. So I should say, something like, I ask you, are you a human being? Now, your answer is, unless you are being facetious, your answer is not going to surprise me. Because the very fact that, I can see you pretty much, typically these are rhetorical questions. Saying, are you a human being? I mean, pretty much you are not expecting a answer back, right? So this is like what you answer won't surprise me, right? Because I know you're a human being, right? So the information content is going to be pretty much 0. Okay? But suppose you are playing this game on the computer where you are querying, and this used to be very popular when we were in IISc in our PhD/postdoc days. So at that time, the talking over this computer was a new thing, right? So you'd play this game all night where you're suddenly in some chat room or something, you're having a conversation with someone, okay? And for whatever reason, I think it reveals the mindset of PhD students. The kind of a very, very common thing would be someone masquerading as a woman trying to chat up another man, okay? Basically, you're having fun because you're leading this man completely up the wrong tree, and then you reveal, ha, like, fooled you, right? And so the question is like, over this entire conversation, basically, one is trying to fool the other person is trying to, figure out whether it's a genuinely, person of the opposite gender or person of the same gender, right? And so, this is pretty much, once the answer is revealed, it is pretty much a surprise because you have no clue who's on the other end, and the other person is deliberately trying to fool you. So it's a genuine surprise when you get to know the answer. So, it looks, I'm sorry for using this formula, but it's just to show you that there's no magic involved here. You can actually calculate exactly how much is the information content of a given, sequence. What you have to do is ask that suppose the variable, what you're writing down, these can take on any value between, let's say, 1 to n. So in here, you have letters, and these letters can take on any of the characters A up to Z, and so you have 26 possibilities, plus, let's say, space. So let's say you have 27 possibilities, all right? And let's say, you know what is the probability that a particular variable over here occupies, let's say, or takes down the value A, takes on the value B, takes on the value C, and so on. Suppose, each of the spaces has an equal probability of, being A, B, C, up to Z and space. So then you would say that, there are 27 possibilities of this particular space, being a particular value. So it could be A, it could B, it could be C. So then if it has exactly the same probability of taking on any of these values, what is the probability that it will take, let's say, value A? Any answer? Okay, sorry, I think I might have not phrased the question correctly. So each space has equal probability of being A or B or C ... Z and space. What is the probability that a particular place will have the value A? 1 by 27, because there are 27 possibilities, and I say that they're all equally likely. Okay? So in the simplest setting, you can say that the probability of the space I taking on the of the particular space I taking on a particular value A is, let's say, 1 by 27, and then you essentially ask, okay, so I suppose I have this entire sequence of 23 letters. Okay, I also have to add the space. So there is 1, 2, 3, 4. So add 4 to it. So there are 27 spaces in all. So basically, you do this sum over this 27 spaces. Each of these 27 spaces has a particular, so you ask, what is the probability that you will have this particular message? Now, if each of the spaces are equal probability of being A, B, C up to space, then what will it be? The first space has a probability of 1 by 27 that it's B. The second space has probability 1 by 27 that it's E. The third space has 1 by probability that it's space, and so on. So now you write 1 by 27. Okay, this is logarithm. Are everyone familiar with logarithm? So this is something which is taught in high school. So hopefully everyone is familiar with logarithm, right? No? Yes? No? Okay. So in case you don't know logarithm, so this is basically something which the moment you have to do calculus, you will have to come up with, encounter logarithm, because you realize that the derivative of an anti-log, namely e raised to power something, is basically the function itself, e raised to something. And you ask, okay, interesting. So what about a to the power x? And you take derivative and you find that, okay, it's not a to the power x. So it is a to the power x log something, right? So the only way that it can actually give you back the exact function itself is if it's exactly this number e raised to power something. So it turns out that if you take log to the base e, that gives you the natural logarithm. But you can take log, to the basis of anything. So you can take log to the basis 2. Okay, so I understand that some people may not be getting it, so maybe I'll take a different tack. Okay, so suppose I say that log to the base 2 of some number n is b. Okay. Now, this is essentially same as saying that 2 raised to b is n. Okay. In other words, suppose I'm looking at what is log 2 8. Can anyone tell me what is log 2 8? Log of 8 to the base 2? Everyone agrees? If you have any question, if you have any doubt, just ask. Because I've just given you the formula here. How do you find the log? It is such that 2 raised to that power will give me the number whose log you're taking. Okay? So this is basically what you're doing. You're doing the anti-log. Okay? So 2 raised to something is, let's say, n. And if you take log on both sides, you will basically get b on this side, and you get log to the base 2n on the other side. So why is Nisha saying it's 3? Very simple. What is 2 raised to the power 3? That means 2 times 2 times 2. 8, right? So if it is 8, now I take log 2 on both sides. Okay. So if I take log to the base 2 on this, so we know that log 2 to the power anything, x, will just give me x. Okay. Because this means that log is just an operation which tells you to what power this particular number is raised to give you a particular value. So it just gives you the power x. So then, since 2 to the power cube is equal to 8, and I know, so then I know that log of 8 to the base 2 is basically just 3. Now, if this is difficult, just think in this way. How many yes-no questions do you need to ask in order to distinguish between n possibilities? So let's say there are 8 possibilities. So this could be what? For example, the outcome of 3 coin tosses. So it could be head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, and tail, tail, tail. So 1, 2, 3, 4, 5, 6, 7, 8. 8 possibilities. How many questions, yes, no questions do I need to find the answer? Which of these has occurred? 3, right? So you can also think of this as basically each coin toss has 2 possibilities, head and tail, head and tail, head and tail. So there are total 2 to the power 8 possibilities. Okay? Sorry, what am I saying? 2 to the power 3 possibilities. Okay? And how many yes, no answers do I need to ask? 3. Now what is 3? 3 is nothing but the power by which I am raising 2. So if I know the number of states is 2 to the power something, that something is exactly the number of yes no questions I need to ask, right? And so that's why, and since I can find out this power by which I raise 2 by just taking the log of that number to the base 2, so therefore all I need to do is basically take the log to the base 2 and find out the number of yes no questions. Okay, so now what I'm doing is, okay, I'm multiplying it with the probability of that particular state happening. Why? Because in general, each of the states may not have the same probability. Okay? So now, if I'm asking what is the total information content of a sequence of n places, okay, then each of these places might have different probabilities of a particular state happening. So one particular state where it is certain that something will happen will not contribute anything, right? It will just contribute 0 information. But the next place might have equal probability of A, B, C, everything happening. So that will contribute a very large information quantity. Okay? So that's why it has to be multiplied by P. Okay? So now I take the product of the probability of a particular state happening in that site times the number of yes no questions I have to ask to find out what has happened on that site, and sum over all sites. And that is the overall entropy of that piece of message. Okay? And that will tell you how much surprise do I get when actually the answer is revealed to me. So for example, if the process is known to you, it always has the same final state. So it's a complete biased coin. No matter how many times I toss, it will get head, 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 head. Head, head. I mean, if you toss it n times, it will always give you head. So then there's no surprise, right? So if you calculate this, what will be P of AI? It will be either 1, that is the probability of being head is 1, and the probability of not being head is 0, right? What is log to the base 2 of this? So log to the base 2 of 1 is exactly, right? Because what is 1? 2 to the power 0 is 1, and so therefore log of 1 to the base 2 is 0. Okay? So I know that this is 0. Okay. Now the next part, what is log 2 of 0, is slightly complicated. It actually goes to minus infinity, but the reason why I can still work with that is because you see what you're multiplying it with. You are actually multiplying with 0. So because you are saying what is the probability of being tail, it's 0, times log of 0 raised to the base 2, that is minus infinity. Now since log goes to 0 much slower than probability going to 0, see typically a linear function always goes to 0 faster than a logarithmic function. It's a technical point. If you don't understand, don't worry about it. This is only for those of you who actually are coming from math or a physics background. So therefore, even if the probability of a tail is 0, this will give you a 0. If it's a head, the probability of head is 1, and log of 1 to the base 2 is 0. So 1 into 0 is 0. So finally what I get is basically 0 plus 0 plus 0 plus 0 to as many states as possible. So finally the information content, if it's a completely biased coin which will always come out head, is 0. But if the process has equal probability, so the coin is a completely fair coin. So every time I toss it, the probability half it will come out head, probability half it will come out tail. And let's say I toss this coin n times. Can you tell me what is the entropy going to be? Okay, if the question is not clear, fair coin, toss it 100 times. What is the entropy? Sorry? So just apply the formula. So what is it? So probability of any particular outcome is half. Okay. Log 2 of half. Okay. By the way, what is log 2 of half? Minus 1, right? Okay. and you sum over, and remember there's a minus sign here. And what are you going to sum over? You're going to sum over the number of times you're tossing it. So it could be n or 100, right? Okay. So now that means 100 of these are being summed. So basically you can just multiply it with 100, right? So 100 times minus this. So what is this? So this is minus 1. Okay, did I make any mistakes here? So let's see, log 2 raised to the power log of half to the power 2, so to the power minus 1. Yeah. So sorry, this minus is not there because I just put the minus inside, right? Yeah. Okay. So what do I get? Okay. So that means I get an extremely large quantity of information, information entropy. Okay. So now let's go to language. So if your language is expressed in just zeros or ones in the most efficient manner, then its entropy is going to be the average number of bits that you require per letter of the original language. That means that if you have 26 letters in your original language, then how many yes/no questions do you need to say what letter is that? So essentially you are doing log 2 26. Okay. So you're basically asking this question, and this is the number of yes/no questions that you require to figure out what is the letter that is occupying there. Okay. But that is if every letter is equally probable. But as we already saw, that this is not true for natural languages, right? So careful can be written as CRFL, and you'll still be able to work out that this is actually careful. And this principle is in fact used in Abjad alphabets like Arabic or Hebrew, where you represent only the consonants and you're leaving vowels to be inferred. So question, in that case, why are there even alphabets which use vowels? Why do we need vowels? Why is not every writing system in Abjad? Sorry? Right, but you might argue that, from context I can make out, like careful, carafal is different from careful, right? So I could have argued that, why not put in vowels because it could be read as carafal, but from context I know that it's actually careful. Sorry, there was yeah, let's just come to you. Nisha, I think you mentioned something. Precision, okay. Well, I mean, this is English, the case of English I'm talking about. So you are basically arguing that in English, it's much more restricted. So it can be only ka. Yeah, but then that will argue that you wouldn't be able to actually figure out what this is. If in English, what you're arguing is basically saying that in English, it will be very hard to work out what am I saying here. Yes, of course, you need the context. And clue as to how to pronounce it. And that language is lost. So we don't even know what was the context. See, for a scribe, this was not a problem. The scribe was not writing for posterity, right? The scribe was just writing it so that another person in another part of the empire would understand it, right? And they share a common context, right? And so the scribe thinks that, this is common knowledge. Why should I even bother? So, just basically sends this information across. But to us, the original language is lost. It's now extremely difficult to work out the full context and thereby actually infer what were the vowels sounding like. So this is a major problem in often trying to figure out what ancient languages would have sounded like. Yes, but yeah, you're right that through context we know that certain certain consonant vowel combinations are not allowed. Okay, so we know that if it is preceded by C dash, it's very unlikely it will be Ra. Okay, it will most probably be Re, and so on. So this allows us to restrict the possible choices. Okay, but I would argue that actually the main reason why we use redundancies is because there is an enormous tendency of messages getting garbled while they are being transmitted. Okay? And famous example of this is the game of Chinese whispers. How many of here have played Chinese whispers? Okay, so for those who haven't played it, it's a very simple thing. You can in fact try it out this evening in dinner. So the idea is you sit in a circle, okay, and one person whispers some message to the ear of the person immediately sitting beside them. Let's say, pass it along, reading Sanskrit is essential. And, you say it in a very, very low tone so that others don't hear what was the message. And so this person, whatever he or she hears, then passes it on to the next person and passes on to the next person and so on. Finally, it comes back to the person who started this message. And the question is, how garbled will it be? Very often it tends to get completely garbled. Your original message, especially if it works best if you have a very long chain, then it becomes really funny what the original message actually turns out to be. Okay? Now, this is a problem in almost any kind of communication in reality, not just for human communication, but also if you're sending information across telecom channels. So there's a lot of fluctuations which happen, so the input signal may actually differ quite significantly from what you get in the output. So for example, let's say you're sending this binary message, and at some point you lose a 1, okay? And at some point, by mistake, this 0 is converted to a 1, so you get this message. And then finally, at this point, let's say by mistake, some fluctuations has happened, which the machine reads as a 1. So instead of 0100100, you read it off as 0011001, which is a completely different message. How to correct for this? In telecom, you do this by essentially providing redundancy. So each bit is repeated thrice. Okay? So instead of sending information as 0100100, you present it as 000, 111, 000, 000, 111, 000, 000. Why is this more robust? So what you do is, when you get the message back, every time you find that this block doesn't have all bits same, you just check which is the majority bit. Okay? So it's very unlikely that the same mistake would occur in the same block. Okay? Of course, you're depending on the fact that these mistakes are happening at random. So you know that the probability of mistake is very small, 0.001 say. So the probability that the same mistake is going to happen to 2 bits within the same block is 0.001 into 0.001, right? So pretty small, right? And so therefore, you basically repeat it. Now, if you say that, okay, the probability of actually a mutation happening is very high, so make it a block of 5 bits. You repeat the bit 5 times. Okay? So the more redundancy you build in, the less efficient it becomes, but the more robust. And so you have this trade-off. Do you want to be efficient or do you want to be robust? Okay. So depending on which is your priority, either the message becomes longer or it becomes shorter. And that's Shannon's great discovery, okay? That you can actually measure that how much robustness do you build into the message such that you can guarantee that it would get transmitted without any problem, without any information being lost. Now, this raises a very interesting connection. So those of you who study myth may have actually seen this wonderful book by Elizabeth Berber and Paul Berber called When They Severed Earth from Sky, and it's a book about what is the history that is hidden in human myths. Do they encode actual historical events? So for example, many cultures around the world have the same myth of the Great Flood. Is there some actual historical content? Okay. It is believed that this flood is actually referring to when the Mediterranean Sea, so Mediterranean Sea used to be a lake, and at some point, during the, I think either early Bronze Age or probably even earlier, the junction of land which connected the North African coast with Gibraltar in Spain, that passage broke down and the Atlantic kind of flooded into this inland sea, and you suddenly had the Mediterranean basin forming. So this cataclysmic event could have served as the Earl legend which formed this myth of the Great Flood. Okay? That's one of the hypotheses that has been proposed. And what Berber et al. Have said in this book is that myths are basically a robust encoding of historical information when you want to send across the information across many generations in a robust manner. So just saying big flood, man died, okay, not very useful. Okay? But if you encode it in a myth, that there was this man called Noah, he received a message from God, build a boat and put animals over there, and it will rain for whatever, 19 days and 19 nights. Actually, I'm taking a mess of it, but you take any Great Flood myth, it will be something of this kind. Okay? But the kernel is that some cataclysmic event happened, as a result of which, essentially a lot of communities got washed away and only very few survived. Okay? And so the point they make is that our oldest written records date back only to about 5,000 years back, but we have been speaking and possibly myth making for orders of magnitude longer, 100,000 years. And so the myths actually could have been transmitting real information about real events, but the only way to preserve information across millennia is to convey it through stories, which essentially become creation myths or other kinds of myths. Okay? All right, now a fun game. Okay. Sorry, Ashraf, I'm really taking away your time. I promise to finish very, very quickly. Okay, so this is a fun thing. Many of you might have seen this movie. It's Lord of the Rings. Okay, how many have seen Lord of the Rings? Okay, not as many as I had hoped. Okay, anyway, in Lord of the Rings, there's this famous sequence in which the kingdom of Gondor has to send a message to the kingdom of Rohan for help because the enemies are approaching their gates. Okay, so of course the steward of Gondor doesn't want this message to be sent. So some the halflings called hobbits have to trickily get into this beacon at the kingdom of the capital of Gondor to light the beacon, and then this message would be relayed from one point to another by soldiers who are guarding this beacons at specified locations, such that every time they see a light at one end, they will light the beacon at their end, and then this beacon will be taken up at the next end and so on. Okay, so this could come wonderfully with sound, but I think something is working. Let me actually just see if I can get the sound. Sir, can I get the sound? Sorry. The sound is really important here. Music is half the, no, the sound, I think you have to do something with the sound. Okay, hold on, let me just come. Sorry, I should have checked the sound before. I think settings, probably something. Oh yeah, sorry. This. Let me just check. It's coming. Should I increase the thing even more? I think yesterday you managed to make it loud. So. Yeah, it's correct. No? Okay. No, I think the previous one was probably correct. Yeah. Okay, so that's the beacon at the capital city. So this is one of the hobbits who's climbing against the order of the steward to light the beacon. He sees the guards are having a fun time, so he manages to get on top. So it's all ready for being burnt, and that's of course Gandalf, the wizard, who sent the hobbit to light the beacon. Oh, okay. That's the sound we want, right? eventually they will ride to the rescue of Gondor. Question, what's the information content in bits? Huh? Sorry? Sorry? It's 1 bit. Are the enemies attacking or not? So, so it turns out that this is actually pretty much what Romans used to do. You know, they used to have this huge number of beacons ready for, you know, informing of enemy movements. And James Gleick has a wonderful point about it. It says that to transmit this 1 bit required immense planning, labor, watchfulness, and firewood. All for just transmitting 1 bit, but a very important 1 bit. So this is, you know, if you're a Lord of the Rings geek, there's this wonderful book on Atlas of the Middle Earth, which is where I've taken this map from, who actually work out what is the distance in miles and how long it takes for the message to be actually passed across. Okay. All right. So okay, I'm very much out of time, so I won't go into this how you interpret entropy as a measure of information. You can watch this movie, which actually video on YouTube, which gives a wonderful way, you know, explanation of how we can use this to essentially interpret the content of information. Let me just go on to, like, you know, talking about something I've already talked about before. So remember this dancing men message. So if all the letters of English had equal probability, then each letter would have an information content of 4.7 bits. But, you know, all letters do not occur with same probability, and that is this information that Sherlock Holmes used to decipher this, right? He knew that all letters do not occur with equal probability. So if you look at the frequency of letters in English, where they occur, you see that, you know, certain letters have a very, very high probability of appearing, and so you will have less surprise if you find that this is E compared to, let's say, if it is X or Z, because these letters occurring would have an extremely high amount of surprise. And so you can ask, okay, what is the entropy of English? It's clearly not 4.7. So if you use letter frequencies that you know that E occurs much more frequently than, let's say, Z, using those occurrence frequencies, you can bring it down to 4.1 bits. But even this actually ignores the fact that if you have C, with a very high probability, it will be a vowel, A or E or I. Okay? So if you know what is the letter before that, it already reduces the, you know, randomness, or it reduces the probability of, you know, you having a certain character after that. So you have to consider what goes before, and so instead of a single letter occurrence, you have to look at n-gram occurrences, right? So if you take into account bigram or trigram occurrences, you can basically find that the entropy is actually more like 3.3, and then you can actually reduce it further by knowing that typically words occur with unequal probability. So for example, the occurs much more often, of and to, all of these occur very high, with a high probability in any given piece of text. But words like really or quality occurs with relatively low probability. So this is what is known as Zipf's law, that probability of the nth most frequent word actually goes down as 1 over n. And using this information, you can actually show that the entropy of English is more like 2.6 bits per letter. And you can actually now go on to ask, okay, is this differing from language to language? So for example, in 1935, the American linguist George Zipf actually looked at this, what he called the law of abbreviation, where he found that the more frequently a word is used, the shorter it tends to be. So this is very much like Morse using a code such that the most frequently used letter has the shortest representation, a dot or a dash, and the least frequently used letter has a very long representation. And he argued that this is because of this competing pressure of communicating accurately, that is, you want your information to be robustly transmitted, but also at the same time efficiently. So you want to have it as short as possible. So this he called the principle of least effort. Now, this is basically what Ashraf will be talking about. So Ashraf will be using the concept of entropy in his talk today, but tomorrow he'll be showing how, by using a kernel lexicon of recurring segments, so this is done for English and this is for Indus, you can actually show that there is a Zipf's law which holds regardless of whether you're looking at word frequency or whether you're looking at letter frequency. And in particular, he's shown that words, that is, a combination of these frequently occurring sign clusters, which we call motifs, all words, regardless of what language you're looking at, tend to be roughly using the same number of motifs. So if you're writing in Chinese, typically you'll be using 3 ideograms. If you're writing in English, it might seem like you're using 10 letters, but most of these letters actually are not occurring independently. So if you look at which of these letters occur together with a very significant probability, you'll find that clusters of 3 letters or 4 letters occur with a very high probability, so you can call them motifs. And a typical English word would have roughly 3 sign clusters making it up. And so if you measure a word length in terms of the number of motifs, you can find that all of the languages that we studied typically peak around this. Whereas if you look at word length in terms of sign, they span a huge range. So they can go from, let's say, 2 signs all the way up to something like 14 signs. So there's a probability distribution. On the other hand, if you look at random, so if you look at, if you take each of these systems and you randomize them, you find that word length, whether you measure it in terms of the actual signs or whether you measure it in terms of motifs, are correlated. So large words, long words in terms of signs would also be long words in terms of motifs. But if you look at real languages, it turns out that they have roughly the same length in terms of motifs. So this is basically a pre-view of what Ashraf is going to talk about tomorrow. All right, so I will not take up more of Ashraf's time. He's already looking at me daggers. No, Ashraf, you don't have to smile. I know inside you're boiling, but please, I'm really sorry. Okay, so thank you. I'll do it.
Okay, so I think it will take little time to set up my, open my computer. Hope you guys has energy, tired or energized? Okay, good. So people who survived till now, it means that you people are really passionate. So by the time my computer is being open, so, Achha, by the way, Sitavra had given you one faster's disk to look at it, right? I know one person. Anybody else get chance to look at it? What was the direction of? Actually, I am. My talk is going to be on that. So actually, I'm going to talk whether computational method can help to decipher, to infer the unknown. The directionality of unknown in script. How, so can you, so who, okay, who got chance to look at it? If not, why don't you open your computer, Wikipedia is having that faster's disk. Just type the Wikipedia and check faster's disk, and can you just guess it? Whatever it is, please. And I need, yeah, so I'll ask you. So I'll ask everyone actually. So what is the opinion of historian or epigraphist. Just Wikipedia will have that page, first toss the disk, and just check. So, okay, I can give you clue that even Wikipedia has written that what is the direction, whether inward or outward. Though, but you can come up with your own logic, why you are thinking. I'll ask everyone. So just give me a moment. I'll just sorry. Okay, so yeah. So okay, as I said that I'm going to talk on that. So first, what is your opinion on this? So it's so far. Can I just maybe rub this? You can just go to what's called Wikipedia, open it. You can just even the same thing. Yeah, anyway, it's visible. Can anybody say, see here, the directionality is, there is two possibility. Either it is inward or outward, right? So outward is this. Let's say it is outward. Or it is inward. Towards center. So who thinks it is inward? One. Do one thing. So please tell your name and say the reason. Just one reason. You are saying inward, right?
Yes.
So let's say you are inward one person. So can you say your name and tell me the reason?
My name is Abhinav, and the reason I felt the orientation of two symbols were off, and they would seemed appropriate only if it went from periphery to center.
Okay. So next, who thinks inward?
Inward but outward.
You are outward.
Yeah.
Okay. So okay.
Writing has a general flow. We write with a flow.
Okay.
And here that flow is signified by the faces which are turned to a certain sign of outwardness. So that's why.
Okay. Yeah. Next,
My name is Asim, and I think it's outward
outward.
because I also feel like there's a general flow and it's
Okay.
from out into out.
Okay. And next,
I am Ratan. I also think it is going to out
uh-huh.
because of the faces are towards out.
Okay.
I'm Ritesh. So I also feel that it's going outwards because it looks like they have put a line at the end, which might be the end of the statement.
Mm-hmm.
I believe side A is outward and side B is inward.
Oh, I have to make another category. Okay. Side A is outward, right?
Yes, outward.
and side B is
Inward.
in. Okay. Next, anyone?
You should ask him as well. I think it's outwards because of the face
I do.
reason, the orientation of the face.
Or with the interest of time, we can just, maybe we can just take the hand raise things. That will be easier. So how many, who else thinks outward? Can you just raise your hand? 1, 2, 3, 4, 5, 6, 7, 8. So 8 more. Okay. Inward. 1, 2, 3, 4, 5, 6. 6, okay, plus 6, okay. Okay, so this is the case for something which is we don't know, okay. Even for Indus, we already, majority of people are saying based on the, what's called archaeological evidence is saying it's right to left. But yesterday, if you remember his Dr. Subramaniam's talk, he was saying that people have claimed that left to right also. So now, can you see whatever you have come up with the reason? Can you tell me what is the? Is there any problem in this answer? What is the major problem in this answer? Exactly. There is no consensus. Almost 50-50. Everything, see, everyone has their own argument, right? If you can come up, you can give lot of reason for why you are favoring this. Somebody will counter this. So the whole problem of these methods is this. So, and that is true with Indus also. So this is the place where the computational method, the people like who have computational background has the role. They can jump and come up. Is there any solution? Is there any objective solution? It's kind of some one-shot solution. So why it's needed? Because we know that the directionality is very important to decipher anything, because it needs, because if you are enter into wrong direction, obviously your whole effort will is a waste of your time. So directionality is very important. But at the same time, we cannot do random cases, right? So because we don't know why, what cause the directionality of any writing system, it's completely depend on the history of it. So it may, so let's not go into that. Because most of the writing system we know these days is left to right, right? And all the Semitic languages is right to left, whether it's a Hebrew, or Arabic, Persian, or whatever it is. But there are all Mandarin languages top to bottom, right? But even there are other random, other text, which is even bottom to up, is Ogam. It's right, it's bottom to up. Not even that. There are examples. Bostophedonis writing is that just first read one side, then flip the whole plate and read again, then flip the whole part, and then read it again. So the point is, in your around in the world, all possible things is available. So you cannot guess. You say that okay, this is the tradition. No, tradition is everything. Every type of things is available. So, and with this kind of situation, when we are dealing with this kind of situation, we need some kind of computational methods. We need some kind of robust method. So, the point is, what kind of robust, what kind of things we required. So, till now, whatever you have answered based on a somewhat what archaeologists used to do. But even there is no consensus among them. They can see something, other people can see other thing. So for that, here is the computational methods comes in. So for that, what we did is very small step. So what we did, that we took English, you can just say list, dictionary, just focus how many words start with A, how many words start with B, how many words start with S, and so on. What will you get? You will get some kind of this distribution, a frequency distribution, nothing else. And this asks same question, how many words end with A, how many words end with B, and so on. You will get just another distribution. Which I am saying here left and right, just ignore the upper one. This is the left, this is the right one, in English case. So just by looking these two, can you guess what is the difference? Is there any similarity or difference? Please come on.
Or if you are looking at right terminal is the ending terminal, there's less flexibility on the right terminal and more flexibility on the left terminal.
Correct. So it's simply saying that, okay, if you just see this, it's saying that if compared to this, it's uniform. Not exactly, but here almost all later has appeared, right? But in the opposite side, if you'll see, the words are mostly end with either this letter, this letter, this letter, T, S, D, E, G, and something. Most of the letter ends with a particular letter, and rest are, but if you will see the start, it's not the case. Start with anything else, anything from your spectrum. So this is the whole, and same thing, what we, you can calculate through the what's called Lorentz curve. It gives you the same answer. It's saying that, okay, 70% of here, if you'll see this, 70% of your later contribute only just 10% of things. Rest are opposite way. So the point is, the hypothesis is here, why this kind of things? Can you guess why it is happening? See, it's a very common thing. Well, there is one very common thing. When you are meeting someone, often it happens that once you talk with someone unknown, then and we often said to say, hey, are you Bengali? Hey, you are from Bihar, you are from this place, that place. Am I right? Yeah. Why? So what do you feel when you saying accent? What do you feel? Yeah. And can you quantify that difference? Whatever pronunciation, whatever you are thinking? if you will focus the particular tone, that tone is very much dominant at the end of their sound. Right? If you talk typical Bengali, their O is very much at the last end. Right? So the point, exactly this is it. So the point is, when you start your sound, when you start uttering anything, you have freedom of your whole spectrum. Here spectrum is your 26 letter, whatever the sound is coming up. But once you start uttering anything, maybe somewhere your anatomy, your vocal cord plays some role, and you can. It depends. It's restrict you to utter further sounds. Like we know that XY is very common, YX is not. Why it is? Maybe our vocal code is not allowing us, or whatever it is, the linguists can say something better. But there is restriction. So the point is, your initial sound spectrum is very large. Your terminal sound spectrum is very small. Okay. So this is so initially we thought maybe this is in case of English only. So there nothing beyond that. So what we did, we said, okay, let's check other languages. What is happening? So we found, then we start checking, and whatever language we could gather from the internet. And I almost 25, 26 languages I checked it. And everywhere this is the same thing. There is no exception. Irrespective of writing system you are talking about, or irrespective of time, even old, they say Sumerian. So whether it's an ancient writing system, modern system, whatever the language you are talking about. So this is the universal pattern we found. Yeah. Sorry?
Third curve, any? Oh, sorry, all the alphabets, right?
It's
the
all.
Yeah. So that coincides with left in some cases, but in some cases it coincides with right. But the separation between left and right is
ignore. Just ignore it. That
so
depends on the internal structure. So you can just ignore the middle one, the all one. Just focus on the terminal part. What I'm saying, just terminal things.
Yeah, the terminal separation is there everywhere.
Yeah, I agree with you.
But it's still interesting that even though that separation isn't affected, the curve, the all curve, can lie anywhere in between. It
Right. That can lie anywhere. That is true.
But that then it could
No,
mean
it has else. No specific pattern. Still now we haven't found any specific pattern. What exactly that one? But if you will see the terminal pattern, yes, that is very much well defined, well distinguished.
Okay.
Yeah. So, okay. So the point is, so this is the universal pattern we found. And once you have this, what can you do? So then, once you can do the quantification. And quantification, what he mentioned, just now you learned that how information we can use, information theory we can use, the entropy. Even the same thing we can quantify by using Gini index. Gini index is nothing kind of, it's also measure the inequality. Normally it's used in terms of economics and things. But the concept is very well, exactly same thing. So if your probability is almost uniform, so what you need, your entropy will be little higher. So the surprise is high. If your words are ending with particular letter only, so it means suppose if all the words ending with particular one letter, so you don't need information. Entropy will be 0, right? So but here it is not the case. So the point is, so always the start entropy is higher, end entropy is lower. Yeah. So, and you can just make a single quantification. If you will just do the left minus right, you can just get some positive number. If you are positive, if you are saying the left minus right is positive, it means the left is higher. But here, the case is a little reverse. The left is lower, right is higher, but the delta G is negative. So you don't need to focus on this part. You just say that what is the sign. So the negative, here positive. So for a moment, ignore it. Just this, focus on this. So whatever language you are talking about, so what will happen? The start entropy is always higher and end entropy is always lower. So when you will, and in terms of a Gini index, start Gini index is lower and the terminal Gini index will be in upper side. So the point we thought, okay, then we checked out whether it is specific in the database size, whether it's dependent on that. So what we checked that for the robustness, okay, what sufficient data we required. So in case of English, we found that okay, at least around you should have minimum more than 100 numbers, so that you can get sufficiently distinguished between the significant number. So this is only giving you the robustness, okay, robustness of the minimum requirement of the data size. So once you will apply all these things, what you are saying, you're saying, so there is some positive line, there is some negative line. So these, all the languages which lie in the left side is from left to right direction, way right. And this side, whatever is coming on the positive end, it's from right to left. So once you have this map, you can put your any, whatever the unknown writing system you have, and you can get it. And where is that? Indus is right to left, without any ambiguity. So this is the beauty of computational methods. And if you want, you can check your own linguistic data. If you have anything, anyway, we are going to work on, we'll do some hands-on here. So, so we'll see it, how it is working. Even if you want to check what is your faster disk is saying, you can check on your faster disk data also. Though it's not certifying you that, okay, this method is not going to tell you something is language or not. But if it is language, it should follow some kind of asymmetry. Any questions so far? Yeah. Oh, acha, correct. So, yes. So what is it showing here? Suppose what will see you once you what you have. Let's think that okay, you have an English dictionary thing, right? So once you have, so just scramble, calculate your entropy or Gini index, whatever it is, then do it. Just randomize your original dictionary. Just shuffle the, just change the position of each later character grapheme, whatever it is, and then calculate the same thing. Okay, so it will show that it is, then you will get some value, and if this particular line is showing if your data is randomized, if it is your not empirical data, if it's random data, whether you are getting same thing, then in that case you will get 0 value. Okay, but if you see that okay, something is very close to under that bar, it means that okay, the confidence level is not that great. So it needs sufficient data, because I couldn't get enough data, obviously it's limitation of the internet. Yeah, but still it is showing the correct one, but the confidence level is lower. Yeah.
Thank you.
So this line is that. So any other question? Yeah. So sorry, you had some question? Yeah. Yeah.
Segments are ending with the skull symbol. So the point is, it seems like it is going from in the center to the periphery.
So out to in. Yeah. So what we can do, you can now you know how to do this. And in the Wikipedia, I think they have given the numbers also as signs. Use that data, do this technique, and just check it whether it is consistent with your hypothesis or not. Okay. So yeah. So yeah. So the thing is, it is mostly what we know that today, that most of the so our data is our finding is also consistent with the archaeological majority site, right? So we can, in this way we can use any unknown script to get its dictionality. So this kind of work we can use by computational methods. So the conclusion is, the one is the universal pattern. These methods give you universal pattern without any exception. And yeah, you can use to decipher any unknown inscriptions, not only Indus, any writing system. And the beauty of this, that in the whole exercise, you didn't use any underlying grammar or any linguistic information. You did everything just purely based on statistics. Okay, so what we can do right now, so we can do a small exercise. So just take any English word list, and we everywhere it is available in the even in Wikipedia, anywhere, whatever your interest you have, you can take a word list of your own language, any language you want. For simplicity, if you don't want to do anything, you can just take English. Just count the frequency, plot a bar graph, and can you show me just now? So those who don't want to explore too much, what I can suggest you, I can just give me. There are places where you can get the So you can download any text or any word list. Okay, those who don't want to do go anywhere, in Google Drive I have already shared one word list, which is from Google Ngram. Just 10,000, I have just copied a 10,000 word list. You can just copy paste and check what is the frequency. And just try it, and still who doesn't have computer, they can work with me. Those who want to try out by yourself, please carry on and tell me before I do. So what you can do, so it's already I have shared, everyone is an open link. What you can go, you can, so you can, how to share, it's already, sorry, short link. I already is made it to open. Okay, yeah, that is true. No.